Now that we know what parametric equations are and that they create the so-called parametric curves, the next question that we would like to address is how do we do calculus with parametric equations? And first of all, why do we need to know how to do calculus with parametric equations? And the answer is very simple. There are some parametric curves that are functions. That is, they do pass the vertical line test, but they cannot be expressed in the form y equals f of x, meaning, and I'm talking about the curves like this, the cycloids, right? So for example, if you attach the piece of bubble gum to the wheel and watch the trajectory of it, it will create this curve, which is a function but cannot be written in the form of a function as y equals f of x. And for instance, if you want to find the trajectory, not the trajectory, but the length of this arc, you won't be able to do this because it's not a function. If it was a function, then we would have been able to find this area as an integral. Like, let's say if this was a of b, we would find this as the area of a function. We would be able to find the slope of the tangent line at a point C as a derivative of the function at this point. We would be able to find the length of this arc as an integral of from, let's say, d to f is not a good letter, e as 1 plus derivative of f. But since we don't have this function, but we do have we don't have an expression in the form of f of x, but we do have a function. So the question is, how do we answer all these questions? How do we answer all these questions for parametric curves for which we cannot express it as a function? So this is the reason why we are getting into this topic called calculus with parametric equations. And before we continue, let's kind of summarize what we already know. So we know, what does it mean to do calculus? That means we know how to answer the following questions. We know how to find the slope of the tangent line at some point. So if you know how to answer this question, that means you know how to do some calculus. We know how to determine the concavity. So concavity could be either up or down. So if you know how to determine analytically the concavity of a function at some point, then you do know how to do some calculus. If you know how to find the area between the curve or the graph, and in particular maybe some axis, x or y, or maybe another graph, then you do know how to do some calculus. So these are again some interesting calculus questions that we learn how to answer for y equals f of x when it's given to us. And if you know how to find the arc length, then it's also part of calculus. And one last thing is, if you know how to find the area of the surface of revolution, around some axis, it could be the coordinate axis or could be some other line, then we answer this question also using the means of calculus. So let's review the answers to these questions that we know when a function is given to us explicitly. So how do we find the slope of the tangent line? Well, that's literally the meaning of the derivative. So we find the derivative and we evaluate it at this point. Alternatively, we can use the Newton notation and write it this way. How do we determine the concavity of a graph? Well, that's the meaning of the second derivative, and if the second derivative is positive, so again we can write it either like this or like this, and if it is positive then it's concaved up, if it is negative then it is concaved down, and if we have 0 then we could potentially have the point of inflection there. How do we find the area between the graph and the coordinate axis? Well, we integrate the function, for example, in x-axis, so from, well, or within some domain. How do we find the arc length? We also integrate over some domain. We integrate this piece of arc length, and we use this notation, but we understand that ds stands for this, and this can be interpreted as either dx dy, so we can, it looks like we're pulling out dy from the radical, or we can pull out dx, and this gives us the two different formulas for the arc length. And finally, when we're finding the area of a surface of revolution around some axis, we're integrating 2 pi y ds if we rotate around the x-axis, and we integrate 2 pi x ds if we have a rotation around the y-axis. So there are two parts in doing calculus with parametric equations. We're going to break it up into differentiation and integration, and the goal would be to answer all the same questions for curves that are given to us like this in parametric form. So this is the goal of this section. We're going to learn how to do calculus with parametric equations.